Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 19. Today we will talk a little more about the PNP transistor and in particular its small signal model, and then we will enter the interesting world of amplifier design. But before we go there, let's take a look at what we covered last time. Here's a quick review. We saw last time that the early effect in a bipolar transistor translates to a change in the collector current when the collector emitter voltage changes. And we wanted to include that in the small signal model, and it turned out that it lends itself to a very simple resistor that we add between the collector and the emitter, and we call RO. That completes the small signal model of the bipolar transistor. So what we do remember is that GM, R-pi, and RO are all bias-dependent quantities. GM is equal to IC over VT, IC being the collector bias current in the absence of signals. R-pi is beta over GM, and RO is the early voltage divided by IC, the collector bias current. So we have to bias up the transistor, bring it into a suitable condition for amplification. If we have no bias in the transistor, no collector current, no base emitter voltage, no collector emitter voltage, then the transistor is dead. It has no amplification ability. All right, then we looked at the PNP transistor and we said that it operates in a manner similar to an NPN transistor, except that all of the polarities are swapped. The transistor consists of a P plus emitter, an N base, and a P. Okay, this is actually incorrect here. So this should be P and this should be N. So a P plus emitter, an N base, and a P collector. So to ensure that the base emitter is forward biased, the base has to be more negative than the emitter, in contrast to what we saw for the NPN transistor. Similarly, the collector has to be more negative than the base. And we said that the symbol of the transistor incorporates an arrow pointing inward to distinguish it from the NPN device. And oftentimes we actually draw this device with this emitter on top because in electronics we would like to show positive voltages on top of the page and negative voltages on the bottom of the page. And this can be a source of confusion. So the top terminal is not a collector all the time. It just depends on whether there's an arrow on it or not. So we saw that the large signal model of the PNP transistor is very similar to that of the NPN transistor. And when we draw it out, it looks like this, again with the emitter on top. If we don't like it, we can always flip it over so that the emitter is on the bottom. We need a diode between base and emitter to account for the base current, and then we have a voltage-dependent current source between collector and emitter to account for the exponential behavior. And these voltages have to be carefully placed here. This would be VEB, not BE, and this would be VEC, not CE, if we want to include the early effect. All right, so let's pick up from here the large signal model of the PNP device and see how we can develop the small signal model for the device. So today we're going to talk about that, then we'll make some introductory remarks to amplifier design, and then we will eventually arrive at one amplifier topology, which is very common, and we call that a common emitter topology. So let's talk a little about the small signal model of the PNP transistor. So I would like to refresh your memory that this small signal model of a transistor tells us what happens, what the transistor does when it is biased And when a signal comes in to create small perturbations in the collector current and the base emitter voltage, etc. So the small signal model only tells us what happens when there's a change, a small change in these quantities, in the collector current and so on. So when we consider the changes that occur in an NPN transistor, and then we look at the changes that occur in a PNP transistor, it turns out that they are identical. So if the base emitter voltage of an NPN transistor becomes more positive, the collector current changes in some direction. Now, if the base emitter voltage of a PNP device also becomes more positive, the collector current of the PNP device changes in the same direction as before. So without going through the details, I will just state here that the small signal model of the PNP device is identical to that of the NPN device. Identical. I repeat this because students often make mistakes about the small signal models. So I will write here, in fact I will write it in red so that you will always remember, identical to small signal model of NPN transistors. I guess I'm not quite consistent. I'm using lowercase here and uppercase here, but you know what I mean. Okay, so again, I'm not proving this. The proof is not that hard. You just have to go through the small signal derivation of the PNP device as we did for NPN and convince yourself that the results are exactly the same. So let's draw that. So for a PNP device, we have the same exact small signal model as for the NPN device. So if this is the base terminal, and this is the collector terminal, this is the emitter terminal, we still have R pi here. And we still have V pi. V pi denotes the change in the base emitter voltage. So V pi is here, positive up here, negative here. It has not changed. Okay, so V pi is a change in the voltage, not the absolute base emitter voltage. The absolute base emitter voltage in NPN is positive. In PNP, it's negative. But this represents only when a small signal comes in and it makes a change. Similarly, this arrow is pointing from the collector to the emitter. And its value is given by Gm times V pi. And finally, the output resistance is denoted by RO here. So the models are identical. No change at all. Of course, what may happen is, as I said, sometimes we draw the PNP device upside down in the actual schematic because we tend to place positive voltage on top of the page. And that should not cause confusion. So, as an example, let's consider a little circuit here. We have a PNP device like so, and there's a microphone signal here, and there's a battery here. We don't understand the details of the circuit, and that's fine. We're just trying to draw the small signal equivalent circuit of this amplifier or this topology. So we call this V0, we call this V1. We have a microphone signal, there's a PNP transistor, and it just happens that its emitter is on top. It doesn't have to be, it just happens that we drew it like that. There's a resistor here, we'll call it RE. There's another one here, we call it RC. And we are asked to simply draw the small signal equivalent circuit of this circuit. That's it. We don't understand how it works, and that's fine for now. Okay, so we go ahead and draw the small signal model of the transistors. This transistor. This is the model. The emitter is here. The base is here, and the collector is here. So we just carefully map this transistor to this topology. All right, so let's start. Here's the base of the transistor. The base of the transistor goes to R pi and goes to emitter. Emitter's up here, so I will draw it like this. Again, you have to be careful not to get confused, because the emitter happens to be up here. Then there is a controlled current source from collector to emitter. The arrow points from collector to emitter. Collector to emitter. So we draw a current source pointing from collector to emitter. V pi is the small signal voltage from base to emitter, regardless of whether it's PNP or NPN. So from base to emitter, V pi. Again, in your mind, just turn this upside down. Okay, and finally, we have the output resistance between collector and emitter. So between collector and emitter. And of course, this value of the current source is GM V pi. I just write it down here. Okay, so we mapped the PNP transistor to its small signal model. Now we need to add the rest of the stuff to arrive at the complete small signal equivalent. How do we do that? Well, how about the microphone? Typically, we model the microphone by a voltage source. It's an AC voltage source, if you will. It varies with time. So we have a microphone. So it's a voltage source from here to here. It's a time-varying microphone voltage source, so we don't use a battery symbol for it. And we'll call this V in, or you can call it V mic, VM, whatever you like. Then after the microphone, we have a battery that goes to this top wire. What do we do with the battery? If you remember last time, we said that for small signal operation, where we deal with changes in currents and voltages, constant voltage sources become short circuits. Constant voltage sources become short circuits because their value does not change with time. We are looking for only quantities that change with time. This voltage does not change with time, so its small signal model is a short circuit. It's a zero voltage source. A zero voltage source is a short circuit. So it's always good to just write this here so that we don't forget that this becomes a short circuit. And of course, this is meaning we're for small signal operation. Small signal model. Okay, so we will replace this battery by a short circuit, just a wire. They come up here. There's another wire that connects this point to a resistor that goes to the emitter. So here's the emitter. We connect our resistor RE, and we continue. Now we go over here. We have another short circuit. So we draw a short circuit. And then we have a resistor RC going back to the collector. The collector is here. We draw like so. And that is the complete small signal model. Looks a little complicated, but given that we have analyzed much more complex circuits in our circuit theory courses, this should not be a huge problem. In fact, you can see that there are not that many nodes here. There's a node here, there's a node here. So here we can write two nodal equations and solve it. So it's not that bad. We'll revisit this sometime later. Okay, this brings us to the quiz of the day. I give you another example and I ask you to draw the small signal equivalent circuit. So here's the quiz of the day. And here's the circuit whose small signal model we want to draw. So again, I draw a microphone. You can always just draw it as a voltage source, a variable voltage source. So that's a battery. This is another battery. This is a microphone. We call it Vin. And we have two transistors. Now we have to choose a name for the transistors. For resistors, we call them R, R1, R2, capacitors, C1, C2. What do we do with bipolar transistors? Well, the symbol we use is Q. So we will call this Q1 and this one Q2. I don't really know why people chose Q, but that's the symbol that we use. Okay, our objective is to draw the small signal model of this circuit in the next 90 seconds. Okay, so what did you get? Well, we know that the small signal models of the two transistors are identical, so we'll just go ahead and map each of them to a small signal model. And then we just try to see what the result looks like. Okay, so here's what we have. We start out with Q1. Q1 has a small signal model just like this. So we draw R pi. The only things that I know, I will have an R pi for Q1 and another for Q2. So why don't we give these numbers to avoid confusion? So we'll call this R pi 1 and the voltage across it V pi 1. Then, sorry, let me draw this lower because I will need space for Q2. So let's draw it lower. Okay, let's see. All right, so for Q1 we have R pi 1 with a voltage of V pi 1 and a current source equal to GM1 V pi 1 and a resistor RO1, all comprising our first transistor. Okay, how about Q2? Well, we can just draw the whole thing, maybe upside down, because the emitter of Q2 is up there. So here's how it is. The base of Q2 happens to be shared with the base of Q1. So let's take this terminal here, go to the base of Q2 and call this resistance R pi 2. The voltage that appears across R pi 2 is positive at the base and it's negative at the emitter, regardless of what type of device we have. So we have positive here, negative here, V pi 2. Then, so this is the emitter terminal up here, and then we have a current source. The current source is oriented from the collector to the emitter. So that is the current source, and this value will be GM2 V pi 2. We have a resistor to model the small signal behavior of early effect, RO2, and that completes the small signal model of Q2. Okay, what else do we need to do? Well, it just happens that these collectors are also shorted together. So these collectors are shorted together. And coming from the input, we have a microphone. As usual, we model that by a voltage source. So here's a voltage source, which we call Vin. This battery becomes a short circuit because its voltage is constant with time. It doesn't change, so its change is 0. And it actually goes to this wire, to the emitter, and continues. So it continues, and then it goes through another short circuit. We have another battery whose voltage doesn't change. Voltage change is 0. So that battery goes from this bottom terminal all the way to that top terminal. So it goes like this. And this is the complete small signal model of this particular topology. Okay, this is a little more complicated than this. So if you were to analyze the circuit, it would seem a little complex. Looks like lots of devices in there, etc. But let's take our time and make some observations about it. We will not analyze it at this point, but some observations are useful because they allow us to simplify the circuit. So let's look and see. All right, well, remember that there is a short circuit from here to here to represent this small signal change of this voltage source, this constant battery. So then let's examine RO1 and RO2. What can we conclude? Well, we see that the top terminal of RO1 is shorted to the bottom terminal of RO2, and the bottom terminal of RO1 is shorted to the top terminal of RO2. So we have two resistors, and they share the terminals. These two resistors are called parallel resistors, as you know. So the first observation that we can make is RO1 is in parallel with RO2. Without a doubt, right? So if I were to simplify the circuit, I would just use one of these and write RO1 in parallel with RO2. That would be one nice simplification. Okay, what else? How about RPi1 and RPi2? Well, they share their terminals here. You see that the bottom terminal of RPi2 is connected to the top terminal of RPi1. And the bottom terminal of RPi1 is connected to the top terminal of RPi2. So these two are also in parallel. So RPi1 is in parallel with RPi2. That's great. So what does that tell us about Vpi1 and Vpi2? Well, if two resistors are in parallel, their voltages must be equal. So we can say that Vpi1 is equal to Vpi2. In other words, if you're trying to solve the circuit, you have dropped one unknown. These two are equal, so we don't need to carry Vpi1 and Vpi2 around because we know that only one of them is unknown. All right. Anything else that we can conclude about the circuit? How about these two current sources? This current source is connected from this node to this node. And this current source is connected from this node, the same node, to the same node. So these two current sources also happen to be in parallel. So we say GM1 Vpi1 is in parallel with GM2 Vpi2. If two current sources are in parallel, what do we do? Well, let's step back. If two voltage sources are in series, what do? We add their voltages. So if two current sources are in parallel, we add their currents. So we could actually just add these two, meaning replace the two current sources with one current source. So the point of this example is to show you that when we encounter a more and more complex circuit in our studies, the first thing we should not do is to quickly write equations, write KVLs and KCLs, nodal equations, that sort of thing. We should take a step back, look at the circuit for a while, and try to feel what's going on in the circuit. Try to understand the various mechanisms that are happening, and that allows us to not only understand the circuit better, develop insight into its operation, but also simplify our calculations. Otherwise, you just write a bunch of equations, and at the end you have to solve 5 equations and 5 unknowns. It's very tedious. But if we take our time for a few minutes, 5 minutes, take a look at the circuit and try to make some simple observations, our life will be much simpler. All right, so this was all I had to say about the PNP device, and now we are ready to move on to another interesting chapter in our studies. So let's open a new page. So we'll talk about amplifiers. All right, well, we have some idea as to what an amplifier is. It should amplify. It should make signals bigger in a very simplistic view. Now, we have seen examples of amplification in our previous studies. So if I go back to my Circuitpedia here, I can show you what we accomplished before. So again, we go back to our Bluetooth example, and remember that we had an oscillator driving a power amplifier, and the power amplifier drove the antenna. So we said that the power amplifier, of course, needs to amplify because we need to deliver a larger signal to the antenna for a long range of communication. And then we also saw that, as at least mentioned, that the oscillator itself needs some sort of amplification inside. So that's necessary as well. For the receiver, we saw that because the signal coming from the antenna is small, we have to amplify it before we do anything else with it. So we use a low noise amplifier to amplify it. And it turns out that actually there are some other building blocks here, including the A to D, that need amplification too. So amplification is an essential component in many different types of circuits that we design. Not just amplifiers, explicit amplifiers, but many other circuits that we also face. That's why we emphasize amplifier design so much here. It's not just that you will go out and design an amplifier, it's just that almost any electronic circuit that you want to design requires some solid understanding of amplification. You might have seen operational amplifiers in basic circuit theory, or may not, that's okay. But here's what we observe. If you go and buy an op-amp, operational amplifier, 741 for example, this is a very common type of op-amp. It comes in a little package like this. It has 4 pins on this side and 4 pins on that side. And they give you a diagram of what's inside the 741, and the diagram looks like this. You might have seen the symbol as symbol of an op-amp, and it has 2 inputs, 1 output, and then some other things, power supply, etc. Now, if we go and dig inside this amplifier, there's a little chip inside. The chip is very small, maybe 1 millimeter by 1 millimeter. If we go and look at that chip, we see something interesting. Here's the circuitry that we see inside that amplifier. So you see lots of bipolar transistors. We have NPN, we have PNP. As I said before, typically the PNPs are upside down because we assume this is the positive rail. This is the negative rail, meaning positive supply, negative supply, or just that this is more positive than this. And then we have resistors. We have all sorts of interesting structures. And at this point, we have no idea what these things are doing here. Right? We have no idea. Because we are not familiar with these different structures. You see the structure here, sort of interesting. 2 transistors. This guy has a short between the base and collector. Why do you want to put a short between base and collector? We don't know. And then you see something similar up here, except that these are NPN. Here's a transistor, here's another one, and there's a short between base and collector. What the heck is that? What does it do? We have no idea. Then we have some other structures here. We don't know what this is. Various types of topologies. So my point here is that we have this complex circuit inside this op-amp, inside this package. And we need to analyze it. We need to understand it. Why? Well, it's not just because you might have to design this op-amp at some point in your life, but also if you're trying to use this op-amp, sometimes you need to understand what's going on inside. Sometimes when you're trying to drive a car in a very extreme condition, you need to understand what's under the hood, how the engine operates, etc. So this is similar. Okay, so with all of these transistors, according to the numbering here, we have 20 transistors, right? 22 transistors. So some 10, 15, 20 transistors. How do we analyze the circuit? Do we go ahead and draw a small signal model for each one of them? And then how many KVLs and KCLs, how many node equations do we write? So that's not something we want to do. Because even if we could do that, the result would not be very useful. You end up with the equation this big, and you try to solve that equation, and then what? It doesn't give us any insight into the operation. So our job, while we are studying electronic circuits, is to be able to take a circuit as complex as this and break it down into little pieces that are familiar and replace those little pieces with some simple models in our mind. For example, maybe I recognize this from some study. I can think of it as doing some sort of function, and so on. And if we do all of these, then eventually this becomes manageable. So we will go in that direction, step by step. We will build, analyze, and design little circuits. Not this whole thing, little circuits. So step by step we build these and add them to our mind as a library of different structures. And at some point, when we come back, suddenly things become look more familiar. Suddenly we say, this is called a current meter. This is called a VBE multiplier. This is called an emitter follower. And this is called a emitter follower. This is called a differential pair, and so on. So all of these will become familiar, and we can understand what they do. It is this incremental approach that allows us to understand and feel how the circuits operate. So let me start with design procedure. So how do we go about designing an amplifier? And it turns out that design procedure is not that different from the analysis procedure. So if you want to analyze an amplifier, you more or less follow the same techniques. Okay, so the first step is select a topology. We have different amplifier topologies that do different things. They all amplify, they all make the signal bigger, but they have different properties. So we have to select one. How do we select one? Well, that comes with experience and lots of practice. at the starting point, at this point in our studies, we have no idea how to select an amplifier. Then create proper bias conditions for all transistors. Bias conditions mean what kind of collector current do we want to have? How much base emitter voltage do we need to apply to have that collector current? And so on. So this is necessary because if the collector current without any signals is 0, I have a cough. I don't know why. If the collector current is 0, then the transistor has no ability to amplify. Its transconductance is 0. When the signal comes in, the transistor is dead. The signal you see is just essentially an open circuit. There's no amplification. So we need to bias each transistor, meaning that without any signals coming in, each transistor must be alive and well. Has to have a certain collector current, constant, certain base emitter voltage, constant, and so on. Okay, and the third condition, the third task, is to analyze the small signal properties of the amplifier so this pen is a little crazy again. This amplifier of the amplifier, and see if they are satisfactory. So that's a natural procedure for designing any product, right? We start with some general architecture or topology for that device that we're trying to build, or circuit or product. Then we have to give it the proper conditions for performing that function. And then we have to go and see, when it performs that function, amplification, is it reasonable? Are the results good enough for whatever we want to do? Okay. So, but what do we mean by small signal properties of the amplifier? How do we characterize an amplifier as a good amplifier or as a poor amplifier? So let's talk a little about that. Let me change the color of my pen. So, amplifier. Okay, this pen is a little crazy today. Amplifier characteristics. Okay, so what does an amplifier do anyway? Well, we know that an amplifier should take a signal, a microphone signal, an antenna signal, and amplify it, make it larger. For example, we have a voltage coming in representing the microphone signal, and we would like to amplify that signal. All right, so here's what we are thinking. Here's an amplifier, and let's change the color of our pen back to brown. And this amplifier receives a signal like so as a function of time, and what we are hoping is that it will give us a bigger signal swing. So it will give us larger swings. That's what we call amplification. In most of our studies and most applications, we are interested in amplifiers that receive a voltage and produce a voltage. There are some cases where we might receive a current or produce a current, but for now we'll just assume that. So we have some sort of input voltage, we have some sort of output voltage, and that's what we get. Okay, so as you can see, the first characteristic or parameter that we are interested in is how much we have amplified the signal, by what factor. So how do we quantify that? Well, we take this swing at the output divided by this swing at the input, and we call that the voltage gain to represent the amplification of the amplifier. So we say voltage gain is equal to output swing divided by input swing, and in both cases we mean voltage swing. So that's the definition of voltage gain. Of course, for now we're dealing with only small signal quantities, meaning that this is a small change, that's a small change, and so on. So these are all meaningful quantities. Okay, we have a symbol for voltage gain, and that's A sub V. A represents gain, and V is voltage. So that's voltage gain. For example, we say the voltage gain of this amplifier is 10, and that means that this output swing is 10 times this input swing. How much gain is good? Well, you could have a gain of 4 or 5 in some cases. You could have a gain of 100,000 in the op-amp that I just showed you. The 741 op-amp has a gain of 100,000. So we have several orders of magnitude in the gain range that we have in our designs. Okay, that's one of the characteristics that we care about when we design an amplifier. The higher the gain, probably the better, because we quickly go from a small signal to a large signal, a small signal to a larger signal, so that we can use it for whatever we want to do. Maybe this signal is coming from an antenna or from a microphone. So if we amplify it a lot, it might be better. What else? Well, another parameter is power consumption. Remember that when we have an amplifier, we have a transistor in there, the transistor is biased. Even when there's no signal, there's a transistor here that needs a current. And that current is coming from our battery. So even without any signals, this amplifier is draining the battery. So you say bias currents drain the battery. So that's also an issue. And there are many other parameters. I will just put some dots here that we'll come back to later. But for now, this is one thing that we do need to worry about. Almost any amplifier you design, the first question that you need to answer or analyze is how much gain do we have? How much voltage gain do we have? Okay, so let's go and revisit something that we did a while ago. And I will write the same title that I did before. Let me change the color of my pen to this. I would say, let's build an amplifier. So we have tried this a number of times. If you remember, when we started out looking at the bipolar transistor for the first time, we said, let's try to build an amplifier. And then we said, okay, here's a voltage-dependent current source. Then we went and studied the bipolar transistor. Then we came back and put it in. So what we are not quite sure about is whether the last amplifier that we designed is actually an acceptable amplifier. So let's go back and see where we were a few lectures ago and see if the result is a good amplifier. So here's how we arrived at that amplifier. First, at the very beginning, we said, if I have a voltage-dependent current source, which I called KV1, again, for dependent sources, we still use a circle, not the diamond that you see in basic circuit theory. So, and here's V1. We said if we buy a voltage-dependent current source and we connect this to our signal, let's say our microphone, and then we let this current flow through a resistor, RL, we generate a voltage, V out, which is equal to minus K times RL times V in. That's what we calculated a long time ago. And we said if K times RL is a respectable number, 5, 10 or something, then the output is an amplified version of the input. There's a negative sign here, but it's okay. It just means the signal is flipped. Nonetheless, the output is bigger than the input. The output swing is bigger than the input swing. So that's an amplifier. And in fact, if you're looking for voltage gain is the output swing divided by the input swing. That would be minus K times RL. So in that very simple case, our voltage gain is this, AV. As you can see, the voltage gain can have a negative sign in it, and that's fine. All it means is that if we give it a waveform like so, it just flips it and amplifies it. So it goes like so. Okay, so that's all it means. All right, then we realized that a bipolar transistor has the same ability. This ability is sometimes articulated as follows. We say this device, this voltage-dependent current source, converts a voltage to a current. Converts. So that's the term that we use. Converts. It sees a voltage, generates a current in proportion to that voltage. And in fact, sometimes we use this notation for it, which I hope you will not find confusing. So we say V to I conversion. We say this device, this voltage-dependent current source, converts a voltage to a current. Okay? And voltage to current conversion is denoted by V/I. All right, so what's happening in here? In here is that we converted the voltage to a current. And of course, this translation requires some coefficient because these two have different dimensions. And now we have a current. What do we do with this current? We pass the current through a resistor to create current to voltage conversion. So voltage to current, current to voltage. That's the voltage. So we say the resistor does current to voltage conversion. So we started with voltage from the microphone. We ended up with the voltage at the output. And in this process, we had to convert from voltage to current and current to voltage. Now a bipolar transistor does the same thing. It converts a voltage to a current. We have seen that in the small signal model. We have seen it also in the large signal model. So our next step was to take this whole thing and replace the voltage-dependent current source with a bipolar device. So that's what we did. We took a bipolar device and hooked up our microphone and then placed a resistor here. We call this RL. This is V out and this is V in, and this is our voltage-dependent current source. So again, we have a voltage, we convert to current. There's a current flowing in here. And then that current flows through this resistor and gives us a voltage. So we have V to I conversion and then I to V conversion. Okay, so far so good. Now, when we looked at this more closely, we realized that this circuit doesn't work. Why? Because there's no bias current in the device. If you remember, if we just connect the microphone directly to base emitter and the microphone voltage changes by 5 millivolts, 10 millivolts, this current is very, very small. It goes from 0 to some very, very small number, so it's not really usable. The transistor is dead. So we said, okay, to bring the transistor back to life, we will add a voltage, a constant voltage, in series with the microphone. So in the next step, that's what we did. We added a battery here, and then we went to the bipolar transistor, and then we came to the resistor. Our hope was that when this battery is connected to the base emitter, which we call V0, even when the microphone signal is 0, when this is 0 volt, the base emitter voltage is equal to V0. V0 can be chosen to be some reasonable number, 700, 750, 800 millivolts, and that will give us a certain bias current in the device. Once we have a bias current, we have a certain GM. Here, the transconductance is 0, because the bias is 0. The transconductance tells us how well the bipolar device converts a voltage to a current, right? So here's what we have. IC versus VBE. How well the transistor converts a voltage to a current, a voltage change to a current change. So in the first circuit, we are here. So when the base emitter changes, the current change is extremely small, not very useful. In the second case, we are here. So we have some bias voltage and some bias current. And now, if the microphone signal comes in, it creates perturbation here, creates perturbation here. We have a reasonable amount of current. And that current change flows through this resistor and gives us a voltage. All right, so is this an acceptable amplifier? Unfortunately not. Why? Let's take a look at the circuit a little more closely, and I will change the color of my pen to see why we have a problem here. Okay, well, remember that a bipolar transistor needs to be in the forward active region, and that requires that the base emitter be forward biased. Sure, we have that. But the collector base must not be forward biased, must have 0 or reverse bias on it. So the question is, with this arrangement, am I sure that the base collector is not forward biased? All right, there's another perspective to think about that. We are thinking that in this topology, we have a certain amount of current. Bias current, let's say 1 milliamp. Okay, so 1 milliamp of current is flowing this way through the device. Where does this 1 milliamp come from? Well, it has only RL to flow through, so can it come this way through RL? No, because the current has to flow from a positive voltage to a negative voltage. We don't have anything like that. We can't start from the same point and come back to the same point. That's not allowed, right? KVL doesn't allow it. So we can't have an IC0 1 milliamp here because it doesn't have the right path to flow through. In fact, if there is such a current, let's say we have a current like that, right? Then we can see that IC0 is going like this, right? So I can say that V out is equal to RL multiplied by minus IC0, because the current is going from the bottom to top, not from top to bottom, right? Ohm's law. So if IC0 is, for example, 1 milliamp, and RL is, for example, 1 kilo ohm, then this will be minus 1 volt. Is that a problem? Well, what we are saying is that V out, meaning the collector voltage, with respect to emitter voltage, is minus 1 volt. And that's bad. Remember that the collector voltage has to be at least equal to the base voltage. If the base voltage is, say, 800 millivolts with respect to emitters, then the collector has to be at least 800 above the emitter, certainly not below the emitter. So that means that this condition cannot hold, this current cannot flow, the device is dead. In fact, if you are curious, the device enters saturation, as we discussed before, but the point here is that this device, this topology is not what we want. All right, so the problem reduces to one simple task. How do we ensure that the base collector junction of this device is reverse biased or has zero bias on it? All right, so we'll play a trick. We start from the input network. We keep all of that. Here's what we have. And we go to the base and the emitter. So far so good. Now I need this voltage to be maybe higher than this voltage. And for a current to flow, the current has to go from a positive voltage to a negative voltage. Where do I have a positive voltage? I don't have any positive voltage here, right, in the circuit. So I have to bring a battery, another battery, that provides that positive voltage, and then use this battery along with a resistor to connect to here, RL. Why do I need a resistor? Because I need to perform I to V conversion, right? We had V to I conversion and then I to V conversion. That's why we have a resistor. So that's the resistor. Why do we have this voltage? This is to make sure that this collector can be more positive than this base. So let's check and see if that happens, just with some numbers. Let's say RL is 1 kilo ohm, and this voltage is, for example, 2.5 volts. We call this V1. And let's go and measure things and see what we have. Now let's suppose that IC0 is 1 milliamp as an example. Okay, so 1 milliamp is flowing from top to bottom of this resistor. So the voltage drop across the resistor is 1 milliamp times 1K, that's 1 volt. So we have a voltage drop of 1 volt from here to here, 1 volt. Ohm's law. Okay. All right. How about the base voltage with respect to emitters? So if V0 is, for example, 0.8 volts, and the microphone signal is not there, we're only considering bias conditions, so the microphone signal is 0, we see that the base voltage is also 0.8 volts with respect to the emitter. Now the question is, under these conditions, is the base collector junction reverse biased? Well, 2.5 volts here, 1 volt here. Can I write a KVL around this loop? So let's call this VCE. Well, KVL says 1 volt plus VCE is equal to V1. So 1 volt plus VCE equals to V1 equals to 2.5 volts. This means that VCE is equal to 1.5 volts. All right, so here's where we are. The collector is 1.5 volts above the emitter, as we see here. The base is 0.8 volts above the emitter. Therefore, the collector is above the base. Therefore, the base collector junction is reverse biased. So we're good. Now you can see why this battery is necessary. Without this battery, we would not be able to ensure that the collector emitter voltage is positive, right? So that would be a problem. Okay, so now we have an acceptable amplifier. This amplifier is biased properly by means of V0 and V1. Both of these are necessary. If we don't have V1, we are back here. This is not proper bias because the device does not operate in the forward active region. So we need V0 for biasing, V1 for biasing. And now, when the signal comes in, the signal goes through the amplifier. As we saw before, is amplified and comes out. And it generates a voltage at the output because this resistor takes the current of the transistor and converts it to a voltage. So we have voltage to current conversion by the transistor. Then we have current to voltage conversion by the resistor. And we generate a voltage, and that voltage will be, hopefully, an amplified version of the input voltage. Okay, what we have arrived at so far, this little topology here is called the common emitter topology. So let me pick a color. So I will draw this in a box. This circuit is called the common emitter topology or amplifier. Why do we call it common emitter? Because the emitter happens to be common to the input port and the output port. And these are things that will become clear as we go along. But that's the term that we use. All right. This amplifier is very common in design. It has some nice properties, it has some limitations, and our job is to quantify all of these effects. We need to find the voltage gain of this amplifier. How much is AV, right? We need to find that first, and then some other properties as we go along. All right, our time is up. I will see you next time.